in terms of what we've done so far, this is the topic that we're going to be covering today. Uh, weak acid, weak base, titrations. And for those of you in lab, you guys have that activity this week. Remember, it's not due till Friday. So let me go ahead and blank this page and let me do a simple review. First of all, you should know simple simple stoichiometry. And what I mean by simple stoichiometry is that if you have an acid, like a strong acid and a base, and you have, say, a certain volume here and a certain, usually this is a titration problem. If you have a strong acid and strong base and you have a certain volume here, but you don't know the concentration, but your titrant, and that's usually what's in the burette, you do know the concentration, and you can dictate the volume because of the at the equivalent point when you do a titration, volume is determined. Whenever you have a strong acid, strong base situation, you got to remember that the equivalent point is defined as the moles of the acid, H plus is equal to the moles of the base. That's what happens. That's why the indicator changes color, because what happens is that the indicator is going to, it's a very weak acid generally, and when a base comes in, it doesn't generally release its hydrogen until all the main chemical, the analyte, has been satisfied. Then and only then will it release its hydrogen. That's the indicator. And then in the process of releasing its hydrogen, it changes its conformation and its structure, and that's what causes the color change. So if you saw that diagram of phenolphthalein in the last discussion, that's the key that you've satisfied this requirement. So in general, when you do this type of problem, you want to calculate the moles of your acid, and that generally is the volume times the molarity. And remember that the molarity is moles per liter, and the volume is generally liters. And so you can see that the moles of the acid is determined by the moles times the molarity. Now, we don't deal with liters in titration, we deal with milliliters. So if this right here is a milliliter, then what you will get is millimoles. This right here, milliliter, is 10 to the minus 3. So when you multiply milliliters by molarity, you're going to naturally get a moles that is 10 to the minus 3. So we just call that millimoles. Now the base right here is that, you know, the volume that you've added because you've controlled that in the burette, and you know the concentration that you have. So again, the concentration, moles per liter, molarity of the base times the volume of the base is equal to the moles of the hydroxide. So that's what happens at the equivalence point. And so generally what happens here is, clear this, is that if you want to know the concentration of your acid, the analyte, okay, HCl, but you know the volume, then if you know the moles of the hydroxide for the titration, which is equal to the moles of your H plus, then if you just take the moles of your H plus and divide by the volume of your acid, that gets you the molarity of the analyte that you have. So that's the first part. You guys should know how to do this because this is stoichiometry. If you don't, please review your stoichiometry. But generally, you can solve these type of problem in terms of molarity of the acid times the volume of the acid equals molarity of the base times the volume of the base. Now, this only works when your acid is monoprotic, that is, it has one hydrogens to deliver. If, however, it's diprotic, like sulfuric acid, and you want to neutralize sulfuric acid completely so that it's stripped off its hydrogen, then you got to remember that you have to put in a factor of 2. So that's the first part right there. Okay. The second part is weak acid, weak base system. Now, in this particular part, you're going to naturally have a Ka. That's just by definition. If it's weak, then it doesn't dissociate completely, and the efficiency by which it gives off its hydrogen is determined by the equilibrium constant. So Ka is an equilibrium constant. Remember that we use A to indicate that it's an acid. So the products are going to be H3O plus. If the products are hydroxide, then you're not dealing with a Ka, you're actually dealing with a Kb. Okay, so make sure you understand that when the reaction in water occurs and the chemical gives up a hydrogen to water, so hydrogen becomes hydronium, then it's a Ka, you're forming an acid. If, however, the chemical that you've added to water extracts a hydrogen from water and you form hydroxide, then that's a Kb. I know it seems like it's pretty easy, but that's a source of confusion. You get stuck in terms of, what do I use, a Ka or a Kb? Look at the products and determine whether the product is hydronium or hydroxide. And some of you might even say, well, okay, I've got an acid, NO2. This is a weak acid, this nitrous acid, and I'm reacting it with a base, let's say NH3, and then I get this chemical NH4 plus and NO2. And the question here is, well, what is it? Is it an acid or a base? Because I don't see hydronium or hydroxide. Well, what you have to do there is you have to work out the stoichiometry first. Okay, you have to work out the stoichiometry. Usually you're not given a weak base, you're given, like, say, sodium hydroxide. You got to figure out, this is going to form water. And then if the hydroxide is the limiting reagent, then you're going to have some HNO2 that is in excess. Well, HNO2 is going to, let me clear the screen. HNO2 is now floating in your beaker, and that's going to react with water to form H3O plus and NO2 minus. So what you have to do first, when you have an acid and a base and they're in the solution together, see whether you're going to get a reaction, especially if one of the chemical is a strong acid or strong base. And then figure out which one's the excess, because the excess will then be sitting there, but it's not just going to be sitting there. It's actually going to react with water. And then you can see whether or not you're forming hydronium or hydroxide. Okay, well, when you have a weak acid and weak base, then just, you can make the assumption, especially if your Ka is small, usually in the order of 10 to the minus 3 or so, you can say that the hydronium concentration is equal to the Ka times the initial concentration of your acid. The knot there tells you it's initial. This is initial. And the reason why you can do this is because you're going to assume that the initial concentration of the acid minus X, because remember, it has to dissociate, is approximately equal to the initial concentration of the acid. You're going to say that X is so small, especially since you have a small Ka, that the equilibrium concentration is pretty much equal to the initial concentration. That's the key that makes this equation works. Okay. Now, if you have hydroxide formation, then that's a Kb process. And the Kb is going to equal to the square root Sorry, let me clear that. What you have is the you're going to have some base. The base will react with water and it will form hydroxide. And the conjugate acid, because it's forming a hydroxide, it's a Kb. And what you can do is say hydroxide is equal to the square root of the Kb times the initial base concentration. So these are very handy equations to use because you can cut and to the chase and bypass the ice table and go here, because remember what the ice table gives you. It basically tells you that this right here, conjugate acid over the conjugate base. Okay, so what you're doing in this particular case is you're just saying that the conjugate acid and hydroxides are equal. That's why you have the square root here. Okay, that's why you have that square root. So this term becomes x squared over the conjugate base, and that's Kb. And if you solve for x, you get that. So that's where that equation comes from. It comes from the fact that you're doing simplifying assumptions.
Professor,
Okay.
this was for weak acid and weak base?
Yeah,
No.
weak acids and weak base. Whenever you have a Ka and a Kb, you're going to use those equations.
Okay.
Okay. So it's a shortcut. It's what we do in analytical chemistry, and generally because the acids that you're going to be working with are very weak, 10 to the minus 3, 10 to the minus 4, these things will work. And even if it doesn't, if it's slightly off, then it's off to the 10th. No, it's off to the 100th of a pH. And 100th of a pH is 10 orders of magnitude less. So it's like the concentration would be in the order of to the thousandths of a place. That's why these things are okay. So that's the second part. Let me clear this real quick. Um, the next part is salts. You guys know how to calculate the pH of salts. Remember, salts generally have a metal and an anion, and if the sorry, not a metal, but a cation and an anion. If the cation is generally NH4 plus, then that will react in with water. Water is always in here to produce NH3 plus hydronium, because NH4 plus is a weak acid. That's a Ka. And if you have that, then again, you can just say hydronium is equal to Ka times the initial concentration of NH4 plus. Okay. Now, generally, the anion, if you form an anion and it's a conjugate of a weak acid, something like F minus, or maybe acetate, CH3COO minus, or even NO2, these, if you put a hydrogen on them, become weak acid. But without the hydrogen, they're going to be base. They're weak base. And because they're weak base in water, they're going to form hydroxide, okay? And the hydrogen will donate it to that, and you get the weak acid forming. So let me erase this so there's no confusion. Okay, you get the weak acid forming, and you get HF or HCH3COO or HNO2. The fact is, you get hydroxide, and so you can say Kb is equal to the square root of sorry, not Kb, hydroxide. I keep messing that up. Hydroxide ion concentration is equal to the Kb times the initial concentration of your base. See how you have a base there? That's why I'm using that. That's your base, the initial concentration of the reactant. So the reason why I'm showing you salts is because Later on in our discussion today, what will happen is that the acid, let's say we have HNO2, is going to be completely neutralized by the base. And when it's completely neutralized, that means the moles of your acid is equal to the moles of your base. And the only thing that remains is the anion. And this is just a salt problem. It's called hydrolysis. But you have to recognize that. You have to recognize that these two are wiped out because they're at the equivalence point. But this NO2 now is free of its hydrogen. And because it's the conjugate of a weak acid, it's going to react with water. Okay. So those are the type of calculations that we've done already. So one more type, I forgot. Okay. Let me do this. The last one are buffers. And this is the common ion effect. Whenever you see the acid and its conjugate in solution, okay, the acid and its conjugate. And how do you get the acid and its conjugate? You get it two ways. The first way is by taking an acid. Let's take HF as our example, and we put HF in here. So we're going to have a certain concentration of the weak acid in our beaker. How do we introduce the conjugate? Well, we introduce the conjugate as its salt, NaF. The sodium will be a spectator, but the F will go in here. And now what you have is a solution that has both conjugate pairs. Whenever you have this, you have to calculate the concentration of the acid. You have to calculate the concentration of the base. And then you can use the Henderson-Hasselbalch equation. You can say that the pH is equal to the pKa of this acid plus the log of the conjugate base over the conjugate acid. Just go straight for that. That's the common ion effect. Now, this is one way of getting the buffer. You put in the acid and you put in its salt. The second way of getting a buffer is by neutralizing part of the weak acid. What do I mean by neutralizing? Well, here's what I mean. Let's say that we have HF again. Okay, it's a weak acid. But instead of adding, so this is our beaker. We have HF. But instead of adding F directly, what we're going to do is we're going to introduce a strong base like sodium hydroxide. But we're not going to introduce the equivalent amount of hydroxide. We're only going to introduce a partial amount of hydroxide. So say we have 10 of this and we introduce, say, 2 of that, like say 2 molars or 2 moles, and we have 10 moles of this, then there's only going to be a partial reaction based on the limiting reagent. And so this will be 8 HF remaining, but remember, 2 of that original 10 now forms that. So this will be plus 2. Guess what? We have a buffer. Okay. So because now we have the concentration of F minus from the product of this reaction, and we have the concentration of HF from the fact that not all the HF has reacted, we have a buffer. We can use the Henderson-Hasselbalch equation. All we've got to do is figure out what the concentrations these are, and then we stick it in the Henderson-Hasselbalch equation, and we've got our answer for the pH. So again, as I've said, you guys have already been given the information to solve all of this. It's up to you to put it together. And it's not like random concepts that you just have to remember. These things are actually related to each other. Okay? So get yourself a good notes. Remember the different types of scenarios for acids and bases. And this particular section that we're going to be discussing today will be that much easier. So let me go ahead and get started here. We're going to be talking about weak acids and weak base, and this is a typical titration that you guys are going to have. You can tell right away that what we have here, change my pen, is the analate. That's the chemical that you're analyzing. Okay, that's the chemical that you're analyzing. And you usually have a pH probe in here. Okay, and the pH probe will tell you what the pH of the analate is. And because it's low, you can say that the analate is an acid. It's an acid. Depending on how high that pH is, you can say whether it's a strong acid or a weak acid. And then notice how the pH goes up. That means that the titrant that you're adding is decreasing the acidity level. That means that the titrant is probably a base. Okay, until you neutralize it completely at the equivalence point. And now, past the equivalence point, the dominant chemical is the excess titrant that you're adding. That's why the pH is above 7. So, I already reviewed this for you. The calculations that you will see here, one is the analate only. This is a weak acid, weak base calculation. In the first part of any titration curve, you're going to either be solving for the hydronium or the hydroxide, and you're going to be using the equation, say Ka times the initial concentration of the acid. Because what happens is that you just have the acid. Let's consider the example that I'm going to be talking about is a weak acid being titrated with a strong base. Okay, so if you're going to calculate the pH of just a weak acid, then this is the equation that you're going to use. You know what the concentration of the acid is. You know the Ka of the acid because you know its identity. You can figure out the pH using calculating the hydronium ion concentration first, and then taking the negative log of that hydronium ion concentration to get the pH. So this part you guys know how to do. If you don't, then chapter 16 was a waste, okay? Because this was all chapter 16. The next part is the buffer. And we just finished talking about this. The buffer is the pH equals the pKa plus the log of the conjugate base over the acid. It's always the base over the acid, unless, of course, you're calculating POH, which is equal to the pKb plus the log of the conjugate acid over the conjugate base. But that's the buffer equation that you will use. The next part is the equivalence point. In the equivalence point, let me clear this. The acid is going to be annihilated by the base. The only thing that survived is the conjugate of that acid. It's the only thing that survived. And the conjugate of that acid now is a base, and that's going to react with water to produce hydroxide. This is called hydrolysis. Hey, you can just go straight to this equation. Okay, the hydroxide ion concentration is equal to the Kb times the acid, I mean the conjugate base concentration. How do you get the Kb? Remember that Ka times Kb equals Kw. Okay, and pKa plus pKb equals pKw. And if we're dealing with water at 25 degrees, Kw is 1 times 10 to the minus 14. Okay. If we're not dealing with 25 degrees, then you're going to have to use the exact value of Kw. But that's what the equivalence point is. You got to remember, you don't have the original analate anymore. You have its conjugate because it's been converted. So you have to solve that equilibrium. And then, let me clear this out. We get to the last part, and this is stoichiometry. Okay, what you need to do is you need to calculate the excess that didn't react. When you can calculate the excess that didn't react, then remember that during the titration, the volume total is constantly changing. Why? Because you are going to have the analyte original volume. Remember, you're taking the pH reading. You're taking the pH reading of this solution, and the pH is the hydronium ion concentration over the total volume, the negative log of that. And because the total volume is constantly changing when you are titrating, then this value is constantly changing. So in the stoichiometry, you need to calculate the excess unreacted over the total volume. And when you have that, you have the concentration of the titrant that you've added. And then all you have to do is take the negative log of that. So I hope you guys are able to relate what I just said, because these are the exact calculations that you guys are going to be doing in this type of situation. Okay, so here's what a typical titration curve looks like. Notice that it starts high, which means probably it's a weak acid. Remember that weak acid has very small concentration of hydronium to start with. And so if it has small concentration of hydronium to start with, 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, then the negative log of 10 to the minus 4 is about 4. That's why the pH starts low. And then the thing about weak acids is that they initially go up fast. Here it's sort of gradual, but they initially go up fast, and then it sort of levels off, especially in the buffer region. Okay, so a lot of titration curve will look like this, especially for weak acid. It'll go up and then level off, and then you get to the equivalence point, and that's where the acid, the moles of the acid, is equal to the moles of the base. But notice this is not 7. This is not 7. And the reason why is because the conjugate of that acid, remember the acid has been wiped out by the titrant. The conjugate of that acid forms hydroxide, and that makes the solution basic. That's why that pH is going to be above 7, especially when you're titrating a weak acid with a strong base. It's because the product that forms at the equivalent point is a base. And in water, that base is going to generate hydroxide. And because you have hydroxide, it's going to be above 7. So going back here, you're going to have a weak acid situation. Analyte alone, that's an equilibrium problem. Here, as soon as you start neutralizing some of that acid with the titrant, you've got products being formed. Well, that's a common ion. If it's a common ion, you have a buffer. Use the Henderson-Hasselbalch equation. Then we have the equivalence point. At the equivalence point, all the acids or all your analyte has converted over to its conjugate, all of it. But now it's in a different volume. So the moles are still the same as your original acid, but the volumes change because you've added some titrant. You've got to calculate that concentration because it's not going to be the same as the original chemical that you had. It's in a different volume because the volume changes. I mean, it's a different concentration because the volume changes as you add more base. So you've got to do that. But remember, that's called a hydrolysis problem. You're looking at the conjugate of your analyte and you're calculating the hydronium or hydroxide. In this particular case, because we're dealing with a analyte that's a weak acid, it converts over to its conjugate base. And so you're calculating at the equivalence point, you're not calculating hydronium ion concentration anymore. You're actually calculating hydroxide ion concentration. Because remember, if this is not there, then it's not going to generate hydronium. this is what's present. It's going to generate hydroxide. You're going to calculate the pOH at the equivalence point, and all you've got to do is subtract it from 14 to get the pH. Okay, so that's what's going on at the equivalence point. Then we have let me change the screen view because it looks like it's somewhat small. Let me just blow it up to the PowerPoint. I think that'll make it easier for you guys to see. Okay. See that? Yeah. So moving right along, let's go to the next part. The next part's excess titrant. All you got to do is figure out how much of the titrant went unreacted, because now the limiting reagent is the analate. You've over titrated, you've got excess. You calculate that excess in the new volume, and what you have is you can calculate the pOH, and from the pOH you can calculate the pH as well. So that's a review of what this particular titration curve looks like. For those of you who are in lab, this is exactly what you're doing. So let's consider hypochlorous acid, HOCl. You know that's a weak acid because it's not one of our strong 7. And we're going to titrate potassium hydroxide. Okay, be careful because sometimes I give you a titration and I might give you a titration of calcium hydroxide. You got to remember that if I give you this concentration here, let's say that the concentration of calcium hydroxide is 0.50 molar. Well, the hydroxide ion concentration is not 0.5, it's 1.0, because you've got 2 hydroxide for every 1 calcium hydroxide. So please pay attention to the chemistry. In this particular case, it's monobasic. Potassium hydroxide only has 1 hydroxide to deliver. And your analate is monoprotic, and it's going to be neutralized. So in this problem, I say calculate 0%, 50%, 95%, 100%, and 105% of the equivalence point. Well, what you need to do is you need to calculate what is the 100% equivalence point. And that's because at 100%, the moles of the acid is equal to the moles of the base. So this you can calculate by math, and then you just multiply the 100% volume by 0.95, by 0.5, by 1.05 to get the appropriate volume for those percentage. Okay. So this is the other information that we have. This is your analate. We have 10 mils, 0.4 molars. I make this problem easy because the concentration of your acid and the base are equal. If they are equal, then you know that you need 10.0 milliliters of base to reach equivalence point. Let's say that this wasn't 0.4. Let's say that this particular concentration was 0.8. Well, it's twice the concentration. So that means you need half the volume. Okay? So you can do that on in your head. If the base is twice the concentration, then to get to the equivalence point, all you need is half the volume. Let's say that it's not 0.8, let's say it's 0.2. Well, it's basically half the concentration. If it's half the concentration, then you would need twice the volume to reach the equivalent point. So when it's 2 times greater, you would need half. If it's 2 times smaller, you will need twice the volume. Again, it's just that ratio. Okay? Don't make it harder than it is. Don't make it harder than it is. Anyway, this is our analate. This is our titrant, and we need to know what are the 0. Well, we already know that 100% is 10 milliliters. That means 95% is 9.5 milliliters, 50% is 5.0 milliliters, and 0% is of course 0, and then 10.5 is 105%. Now we know the volume of titrant that we're adding. Why? Because when we have 0, this is just the weak acid problem. Here we have our buffer problem. Here we have hydrolysis. And here we have excess titrant. You can see that just based on the fact that our equivalent point is the marker. Below that, we have buffers, and if we don't add any titrant, then we just have a weak acid, weak base problem. Above that, we have excess. Okay. The other information that I see that I provided here is information about the acid. I tell you what the Ka is, and I tell you that the negative log of the Ka is equal to the pKa. So if you take the negative log of 3.5 times 10 to the minus 8, it's like taking the negative log of the hydronium ion concentration. The negative log of the hydronium ion concentration is the pH. The negative log of the Ka is the pKa. And if you do that for 3.5 times 10 to the minus 8, you get 7.46. In the old notes, I gave you a less precise number. If I just updated this today, I gave you a Ka of 3 times 10 to the minus 8. Okay, I wanted to be more precise here so that you know that because my Ka is two significant figures, my log term, my pKa, has to have 2 digits past the decimal point, because the digits after the decimal point signify significant figures in log functions. Okay, if I gave you 3 times 10 to the minus 8 and that was only one significant figure, then this would be rounded off as a pKa of 7.5. It would only have one digit past the decimal. And I wanted to give you better precision in this discussion. Okay, so let me go ahead and clear this. If these numbers were not clean, then you could easily do concentration of your acid times the volume of your acid is equal to the concentration of the base times the volume of the base. And so what you can do is calculate the equivalent point, equivalent volume. You know what this is, that's given. You can calculate the equivalent volume for the base, okay, using this equation. And then once you get the equivalent volume, then you can figure out the 0, 50, 95, 100, and 105%. And the reason why this equation works, you notice it looks like the dilution equation. Well, the reason why this equation works is because the moles on the left is equal to the moles of the right. And that's what happens at the equivalence point, okay? In a dilution problem, the moles of your analate is equal to the moles of your diluted problem because all you're adding is water, okay? So in the dilution, the moles are conserved as well, but the concentrations are not. Anyway, that's back in chapter 13. Here, we're doing stoichiometry. So let me go ahead and clear this, okay? And these are the volumes of the base that is required, which we already calculated based on the fact that these numbers are pretty straightforward. So let's take a look at the first part, 0%. What did we say? We said that 3.5 times 10 to the minus 8 was our Ka. We said that the concentration of our acid was 0.40 molar. I can just do this without really thinking. realizing that this comes from the ice table, and I can calculate my hydronium ion concentration, okay? And then from my hydronium ion concentration, I can calculate my pH. So see what I did for this particular problem. But that basically is it. Here, I'm always going to show you the basic chemistry, the ice table. You got 0.4 here. You're not neutralizing it at all. So it's going to dissociate in water. It's forming hydronium, so you know it's a Ka. If you look at the mass action expression, we can say that Ka is equal to, this should be an equal, okay? X squared divided by 0.4 minus X. But we're going to make the assumption that 0.4 minus X is 0.4. And so that just becomes 3.5 times 10 to the minus 8 equals X squared over 0.4. If you simplify this math, X equals 3.5 times 10 to the minus 8 times 0.4, the square root of that. Hey, that's just that, okay? And that's just the equation that I gave you initially. When you do that math, it comes out to 1.18 times 10 to the minus 4. And if you take the negative log of that, you get a pH of 3.93. So that's our first data point. That's our first data point. And you see that here, 3.93. That's our starting point, okay? What happens at the 50%? This is a GIF, okay? This is a GIF. You don't even have to open your calculator. pH is equal to the pKa at 50%. We know our pKa is, what was our pKa? Let me go back, okay. Oops, let's see. Our pKa was 7.46. So at the halfway mark, 50%, I know my pH. It's going to be 7.46. Okay. Again, let me emphasize, this is at 50%, not, and I emphasize, not at 100%. 100% is the equivalent point. We're not even at the equivalent point yet. We're only halfway there. And the reason why that works, is the following. Let's look at the chemistry. Here you can see that we've introduced half the moles of the acid. So that means half of this will form product, and the remaining half stays the same. Remember, this is a buffer problem, so the pH is equal to the pKa plus the log of the conjugate base, which is that value right there, divided by the conjugate acid, which is that value right there. Well, these values are the same based on simplifying assumptions. When you have the log of 1, this is because these values are the same, this goes to 1. This whole thing goes to 0. And because it goes to 0, the pH is equal to pKa. Okay, that's what you should always remember. You always get points if you remember this, especially if I give you a titration problem. So don't forget. But even though I tell you this now, some of you are going to say, oh yeah, at the equivalence point, the pH equals the pKa. No, 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 please don't do that. You're just throwing away good points. It's halfway to the equivalence point. I need to emphasize that, okay? Because there's always about 5% of the students when they're taking the exam, and yes, I know it's a stressful situation, and you just reach back and you get your numbers mixed up, but you're gonna say at the equivalence point, the pH equals the pKa. It's not. So anyway, let's take a look at the ice table. You can see that in the ice table, these two are somewhat the same. This one is 0.133 minus X. This one is 0.133 plus X, but again, X is negligible. Why is X negligible? Because the Ka is small. It's 3.5 times 10 to the minus 8. That's a small number. So we can ignore this and we can ignore that. And so when we get to our mass action expression, Ka is equal to x times 0.133. Remember that this is plus x here over 0.133. Remember that this is minus x over here. But because they're assumed to be 0.133, they cancel out. Ka equals the x. X remembers hydronium. It comes from the ice table. It comes from the chemistry. But the Henderson-Hasselbalch equation already gave you that. But again, I want you guys to remember the chemistry, because if you remember the fundamentals, you don't need to remember these equations. Although knowing the equation is good for you as well, because it basically means that you can solve these problems directly. So that's what we have right here. Okay, that's what we have. This is the equation that I derive, and it works out. Or you can do the Henderson-Hasselbalch equation. You can see that these concentrations are the same. That term goes to 0. This should be 7.46. Okay, 7.46. So the pH is 7.46, just as we would have calculated if we did the ice table. Okay, so here is 7.46. As soon as you add any titrant to right before the equivalence point, you have the buffer. And because you have a buffer, you can use the Henderson-Hasselbalch equation. That's the key. Let's take a look at the next part. 95%. That's not equivalence point yet. So we're still in the buffer region. We're still in the buffer. What you need to do, though, is you need to calculate how much reactant remains. So 95% means that we've got 0.40 moles per liter of hydroxide. Remember, that's the initial. The 95% volume was 9.5 milliliters. If you multiply this out, 9.5 milliliters times 0.4, you get 3.8 millimoles. Okay, if you do the math. Well, the original concentration of the acid, excuse my news flash there, I need to turn that off. The initial concentration of the acid was 4 millimoles. If you're going to react your limiting reagents 3.8, then what remains is 0.2. That means that 3.8 product is also formed. Now the total volume is going to be the same for both because they're both in the same beaker. We initially had 10 milliliters of analate, and then we added 9.5 milliliters of titrant. So the total volume is 19.5 mils. So the question was, what is the concentration of the acid and the base at the equivalence point? Well, you gotta need to calculate how much remains here over the total. Remember that these right here, 3.8 is a millimole. I forgot to indicate that. So millimoles over milliliter gives you the concentration. And that's what you see right here, 0.195, 1.03 times 10 to the minus 2. This is the buffer. The pH is equal to the log, the pKa, which we said was 7.46, plus the log of the conjugate base, 0.195, over the conjugate acid, 1.03 times 10 to the minus 2. Oops. 1.03 times 10 to the minus 2. We calculate that term, we add it to 7.46, and we've got our pH of our solution. Again, it's a buffer. Okay, you've got common ions in your solution. That's what a buffer is. So let's take a look at that math. This is the ice table. This is using the mass action expression, making simplifying assumption. And if you do that math, it comes out to the pH of 8.7. pH is equal to 8.73. look at that. That is your mass action expression. And again, we're doing simplifying assumptions here. Okay. This is the Henderson-Hasselbalch equation. Notice all we're doing is using the concentration of our conjugate base and the concentration of our acid. And when we take that ratio and take the log of that and add it to 7.46, we get 8.73. Well, when I did the ice table, I got 8.73. When I did the Henderson-Hasselbalch, it's 8.74. That's good enough. Okay, that actually is pretty close. And if you go out like 4 places out, you'll see how close they are. But that's acceptable. So over here at the 95%, we have 8.73. This is 95% now. This is not 100%. Okay, 95% is still the buffer region. That's why I can use the Henderson-Hasselbalch equation. Please remember that. As soon as you add titrant, part of that analyte is going to convert over to its conjugate. You have common ions, you can have buffers. Let's take a look at the equivalence point. This is 100%. And no, pH does not equal the pKa at 100%. No, it does not. Okay? So don't do that. At 100%, this is what happens. This is the chemistry that occurs. And I want to draw you a picture because I know that some of you are visual learners. We have our acid. And we're adding hydroxide in here. And as we add hydroxide, that acid becomes smaller and smaller, okay? Because it's being reacted with our base. But eventually it'll get to the point where the moles of the acid is equal to the moles of the hydroxide that you've added. When that occurs, then there are no more of that from the initial amount. What you get is all of that converting over to its conjugate. That's the only thing that's sitting in your beaker initially. Initially, I say that because what'll happen next is that is a base, and in a base, it's going to react with water. And because it's a base, it's going to generate hydroxide and the conjugate. So this is our reaction at the equivalence point. We're going to get the conjugate of that original. Remember, our analyte was this acid. Now that chemical is the only thing that survived at neutralization. But now, because it's a weak base, it's going to react with water. It's going to strip a hydrogen on water and form the acid again. But that acid comes from this conjugate base that was formed, not from this original one. It comes from this conjugate base that was formed in that neutralization. And then you're going to get hydroxide. And because you're getting hydroxide, that's a Kb. So you go from a Ka to a Kb. Hey, that's a Kb. We can just say hydroxide is equal to the square root of Kb times the initial concentration of that base right there. We can just do that. It's a shortcut because this is treating this problem right here at hydrolysis as a weak base problem. It's treating it as a weak base problem. So that's the chemistry that occurs. You have your acid, everything gets neutralized. It forms this conjugate, but this conjugate is not going to be just sitting there. Unlike strong acids and strong bases, if you have a strong acid like hydrochloric acid, and we neutralize it with hydroxide, and all you get when you neutralize it is chloride, well, chloride's not going to react with water to form HCl again. Why? Because HCl is not going to form because it's a strong acid. It's not going to associate itself. HCl wants to stay broken. So Cl will never react with water. That will never happen. Cl will never react. A strong acid will never react with water to give you its conjugate because by definition, the strong wants to stay separated. Unlike the weak will go back to its conjugate and give you hydronium or hydroxide depending on what weak species you have. So this is the chemistry, and I hope you guys can see what's going on here. So let me go ahead and clear this. This is what happens. You see how you had 4 millimoles here? Well, you're at the equivalence point. You're reacting 4 millimoles as well. So both of these are 0, but you form products at 4 millimoles. The total volume now is 10 plus 10. 10 from the analyte, original analyte, and 10 for the titrant, because that's the equivalent volume. So if we take 4 millimoles and divide it by 10 milliliters, we can come up with 0.2 molar. Well, again, like I said, you can just take the, this is a KB. You can calculate the KB from the Ka, multiply the KB by 0.2, take the square root of that, and you get hydroxide. Remember, you're getting hydroxide, not hydronium, because this is a weak base. And this is the chemistry. The first part is stoichiometry. You got to figure out what is the limiting reagent. That's why I use this symbol, S, R, and F. S is the start in moles. R is the reactant based on the limiting reagent, and F is your finish in moles. Then from the finish, we calculate a concentration by taking the finishing moles and dividing it by the total volume, SRF. Now, if we have the concentration, that's your initial line in your ICE table. We take the stoichiometry, we solve the stoichiometry, and then that'll be the initial information in your ICE table. See how we have 0.2 here, 0, 0, because the reaction hasn't started yet, theoretically. It's forming hydroxide. Hey, this is a weak base problem. Just do the calculation directly. So let me clear that out. This is it right here. Okay, this is the calculation right here. Notice we're calculating hydroxide. We're calculating hydroxide because that's the species that's present. To calculate the pH, because what you will find out if you do this problem and don't realize that this is hydroxide, you guys are going to get a titration curve like that just drops down like that. If the pH suddenly reverses direction, you know you've made a mistake. And the mistake probably that occurred was you failed to recognize that your new P function is a POH. You have to subtract 14 from that value, and then it'll bring you up there to the equivalence point, okay? Not down here. It'll never be, it'll always be a smooth curve. There's no disruption when you do your titration curve. If you see something that looks like this, you know you've messed up, probably right here, probably right there. Let me clear that. And here you can see that our pH, if you subtract 14 from 3, you subtract 3.62 from 14, you get 10.38. It's constantly moving up. It's constantly moving up. That's the equivalence point. It's called hydrolysis. This is similar to a salt problem. Okay. Finally, we get to the excess. Here, we now add 10.5 milliliters of hydroxide. Well, 0.5 milliliters is the excess. You can figure that out just based on the fact that 10 milliliters was the equivalence point. Well, if you take 10.5 and multiply it by 0.4 moles, you get 4.2 millimoles. Okay, that's that right there. You can see now that this becomes the limiting agent. This becomes the excess, and you've got 0.2 millimoles remaining. What is the total volume? The total volume now is 10 plus 10.5, 20.5 milliliters. 10 from the original analyte, 10.5 from the titrant. So if you take 0.2 and divide by 20.5 milliliters, this millimoles, you get 9.76 times 10 to the minus 3 molar. Hey, just take the negative log of that. If you take the negative log of that, that is equal to your hydroxide. That'll give you your POH, and then you can just calculate the pH directly. It's that simple, okay? That simple. Let me show you how that works out. Okay, here is your excess. It's not an equilibrium because this is a strong base. What we can do is that it's going to be 100% dissociated, 100%. So 9.76 times 10 to the minus 3 will give you 9.76 times 10 to the minus 3 hydroxide. If we just take the negative log of that, remember this is 9.76 times 10 to the minus 3. If we just take the negative log of that, that becomes 2.01. That's the POH, however. We subtract 14. You might ask yourself, okay, I've got hydroxide here, but won't this particular chemical, because it's a weak base, also react with water to give us also hydroxide and the conjugate acid? Yes, it will. So you got hydroxide from the excess that went unreacted there and the reaction from this conjugate. But what you guys are going to see is that this hydroxide that comes from this product right here is so small, it's negligible. Okay, you could ignore it. You could ignore it. And why? Because remember, this is a Kb. It's a Kb because it's forming hydroxide. Look at the Kb value. That's 2.86 times 10 to the minus 7. Ka was 3.5 times 10 to the minus 8 for our original acid. Well, that's equal to our Kb. Kw divided by Ka equals Kw. That's 2.86 times 10 to the minus 7. So, you know, it's going to give you very little hydroxide because it's a small equilibrium constant. And in fact, let me just demonstrate to you. I actually do for you the calculation. This is a calculation of how much hydroxide that chemical will produce. And when you do the ice table and do all the calculation, let me blow this up so that you guys can see. Okay, that hydroxide comes out to 6.64 times 10 to the minus 3 when you do that. Remember our original excess? That came out to 2.54 times 10 to the minus 4. Sorry. What happens is that if you add our original acid, I mean hydroxide, 9.76 times 10 minus 3, and we add it to this second. See how smaller this is? 3 orders of magnitude. So we could ignore this, and we can just say that our total hydroxide comes from this excess right there. And indeed, the pH is practically the same when we add it. So if you're pressing for time, don't bother working on the reaction here, although you should be able to solve that. Okay, you should be able to solve that. Let me go ahead and finish this up. This is your last data point. Your last data point is 10.5. This is the equivalence point. So 10.5 is about here. That has a pH of about 11.99. So this is the excess. This is the hydrolysis. This is the buffer. This is the weak acid problem. Give you a moment to kind of digest that. The problems in this particular illustration are concepts you guys already know. It's just a matter of putting it together. It's just a matter of putting it together. Here's a summary of what I just did. I actually did an Excel spreadsheet to do this calculation. You guys can do the same and generate a titration curve. And the titration curve looks like this using an Excel spreadsheet. This is the equation you would use for this point. This is the equation you would use for the buffer. This is the equation you would use for the equivalence point, and this is the equation that you would use for the excess. So I sort of summarize it for you so you can see that understand the chemistry. I always emphasize that. You need to understand the chemistry. That way you don't get lost and you know where these equations come from. It's so important to understand the chemistry. So this is basically the Excel spreadsheet that I generated. This is it again, okay? But here I sort of show you the titration curve. Notice how fast it rises, and then it levels off, and then it sort of have the equivalent point. This is the equivalence point right here, 10. Halfway to that, 5. If you read the pH here, and the pH is approximately 6.5. No, sorry. This is 8. This would be 7. So it's a little bit above 7. It's about 7.3, 7.6. Okay. And what did we say our pKa is for hypochlorous acid? We said it was 7.46 approximately. So if you have a straight edge ruler and you are more precise, you can see that this value right here, eyeballing it, is certainly within that. When you guys do your lab next week, that's how you're going to determine the pKa of your unknown. You're going to look at the titration curve. You're going to not look at the equivalence point. You're going to look at halfway to the equivalence point, and you're going to read the pH, which gives you the pKa. The equivalence point, remember, the moles of your acid is equal to the moles of your base. Well, if you know the moles of your acid at the equivalence point and you have the mass of your acid, and you divide by the moles of that acid, guess what that gives you? It gives you the molecular weight of your unknown acid. So we definitely use the equivalent volume for your experiment next week, because that's how we get the molecular weight of your unknown. But halfway to the equivalent volume, that's where the pH equals the pKa. So let me go ahead and give you different scenarios here, okay? Because the one problem that we looked at here in detail shows you how to do those calculations. This right here is a strong acid, strong base situation. You've got 20 milliliters of 0.5 molar hydrochloric acid, and you're adding 0.5 molars. You see how both of these are the same concentration? Guess what? The equivalent volume is going to be 20 milliliters of sodium hydroxide. I already know that because these two are the same concentration. So the titration curve for this will start out low. The concentration is 0.5 for hydrochloric acid. If you take the negative log of 0.5, that'll be your pH, because this is a strong acid. So it's going to start out low. It's going to go up, and then at the equivalent point, that's 7, because this is a strong acid, strong base situation. So this is what that titration curve will look like. Let me go ahead and show you that. Here it is. Starts out slow. It goes up. It goes up very drastically, right near the equivalent volume, which we said was 20 milliliters. It is symmetric right through 7, because when it's neutral, the only thing that's going to cause that pH reading is water, and water has a pH of 7 at 25 degrees. So that's your typical acid-base curve when we have a strong acid, a strong base. Suppose we're titrating hydrochloric acid to sodium hydroxide. Well, that's going to look exactly symmetric. Let me change my color. It's going to look exactly symmetric. It's going to do this. It's going to drop dramatically, and then it's going to do that. It's going to be a symmetric of the strong acid, strong base situation. If we have a strong base, strong acid situation, we start out high because our analate would be a base, but we're adding an acid to that, and then it'll drop. So Again, I want to show you the important features of a titration curve. And for those of you in lab, you want to take note of that. You notice as well here that different indicators are going to change colors. And so because very little volume, notice that if we go from like 19.9 mils to 20 mils, which is a very, very small amount, we go from a pH of about maybe 3 all the way to a pH of about 11. Just one drop will cause that. That's why if you were doing this experiment and you reach the equivalent point, your pH probe would actually start drifting, because it's drifting between this range right here. But it's going to be symmetric around 7 if you have a strong acid, strong base. So because very little volume, and remember in our titration, we want the volume of our titrant. Very little volume causes a dramatic change in pH. That's why we can use phenolphthalein, even though phenolphthalein doesn't change color until 9.3. Okay, why do we use phenolphthalein if it doesn't change color 9.3? Because the inflection point is so steep that whether you are at 19.9 or 19.95 molars, it's going to be in that region. So let's take a look at the next curve. This is a weak acid, strong base situation. This is the situation that we just had, okay, that we just talked about. Here we're looking at propionic acid. Propionic acid has a Ka of 1.34 times 10 minus 5. Its pKa is 4.87. Let's take a look at that curve right here. This is our strong acid, strong base situation, this dotted line. That's not what we want. This is propionic acid right here. Notice it goes up initially. It goes through the equivalence point right there. The equivalence point is above 7. Why? Because propionic acid, when it's neutralized, forms this conjugate base, which generate hydroxide. That's why the pH is above 7. But if we take a look at that equivalent volume, this is the equivalent volume. Okay, and we know it's that's equivalent volume because both our acid and our base are equal in concentration. So that means we need 40 milliliters of base to get to the equivalence point, 40 milliliters. Remember, halfway to that, 20 milliliters, pH equals pKa. And what did they say our pH was? It said it was 4.89. I calculate from the literature 4.87. That's pretty close. Okay, that's pretty close. So it goes up and then it sort of levels off, goes up and then levels off. So this is a weak acid, weak base situation. Let's take a look at this is what it would be for different features. For strong acid, strong base, notice how flat it is in the bottom, then it goes up sharply. For more weaker acid, it starts out higher, but then it levels off. And then notice that for each one of these, they all hit the equivalence point at 50 mils. That's where you have the greatest inflection. So my question here is, what is the concentration of the initial acid? And you know, it's the initial acid as our analyte. Okay, actually, not as the my question here is, are the initial concentration of acids A, B, C, D, or F equal to each other, or are they different from each other? Okay, that's my question to you, is are the initial concentration of acid A, B, C, D, E, and F, are they all the same, or are they different from each other? So think about that, okay? And maybe you guys can email me your answer. But the other important feature that I want you to see from this curve is 50 mils is here. Half of that is 25 mils. This right here, where it intersects at each one of these curves, is your Ka or pKa. pKa. pKa for C, pKa for D, pKa for E. There is no such thing as a pKa for F. Why? Because that's a strong acid. Strong acids don't have pKas. They don't have Kas. So don't try and find it. For weak acids, all you've got to do is look at this titration curve, read the pH at halfway to the equivalence point, and you get a Ka value. And then you can calculate a pKa value approximately. Okay. So let me clear that. And this is just a summary of that. If you had a base, it would basically do this. It would drop and it would do that. Depending on how weak your base is, it will drop and it will do that. Okay. And then halfway, you can read the KBs. You can read the KBs halfway. So if you had an inverted curve, then that would be, the analate would be a base and you're adding acid to it, because as you progress in the volume, the pH drops, which means that the hydronium ion concentration gets higher. So this is an important curve, and if you look at the sample test, you see that there was a question in the sample test that had this. This is a titration of a weak base and a strong acid. This is ammonium. So we have, say, ammonium chloride, and we're adding hydrochloric acid to it, for example. Well, we start with a basic solution because what's going on is that this is a base. Actually, we're going to have NH3, okay? And we're titrating it with hydrochloric acid. And because it's a base, it's going to have a high pH. And then as we add more acid, the pH starts to decrease, indicating that it's less basic, it's more acidic. Okay, so for NH3, Kb is 1.76 times 10 to the minus 5. So right here, if this were a pOH scale, then the halfway point would indicate a Kb of 1.6 times 10 to the minus 5. But it's not a pOH scale, it's a pH scale. So you have to do the conjugate. And if you do the conjugate of Kb, you get 5.68 times 10 to minus 10, and that's 9.25. And so if you look at this curve right here, that right there is about 9.25. Okay? Because this is a pH scale. This is a pH scale. For a pOH scale, it would be what? 4.75. If it was a pOH scale, it would be 4.75 because 14 is equal to the pKa plus pKb. Anyway, it's high, it drops to the equivalent, and then it levels off. That's your feature for that. This right here, you can see that there's two inflection points. So this is a diprotic acid, weak acid. You get the first hydrogen coming off right here. You get the second hydrogen coming off right there. Halfway is Ka2. First one is Ka1. Okay, so you can actually read your Kas from, or pKas because this is a pH. You can read your pKas for diprotic system if you can read the curve. And here's the verbiage on that. Okay, this is hypochlorous, not hypo, this is sulfurous. Sulfurous acid, not sulfuric. Sulfuric is H2SO4. This is H2SO3. It's sulfurous acid. It's a weak acid. That's why you have two inflection points. This right here would be a base that can receive more than one hydrogen. This would be the carbonate ion. It gets one hydrogen. The bicarbonate picks up another hydrogen. And so again, you see two inflection points. and you guys should recognize this. You know, this is a strong acid, strong base situation. You start low, it's symmetric around 7, you end up high. This is a strong base, strong acid situation because you start out high, it goes through 7, and it goes low. This right here is a weak acid. You know it's an acid. You know it's an acid because the original pH are always below 7. You know it's a base because the original pH, when 0 titrant is added, are always above 7. You know it's strong because it goes through 7. You know it's a weak because the equivalence point is above 7. You know it's poly because it's got 2 inflection points. So those are the features that I want you to see based on different variation of titration curve. Strong, 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 weak with a titrant being strong, weak base with the titrant being a strong acid, and these are polyprotic because they've got this first inflection point is hard to see. The second inflection point is easy to see. First inflection point, second inflection point. The inflection point are the equivalent points, the equivalent volume. So if you want to figure out what volume was required to remove the first hydrogen, you're looking at that. This is the volume required to remove the second hydrogen. So that pretty much is chapter 17, okay? This particular section pretty much summarized what you guys already learned from buffers, common ion, and then all of chapter 16. So that pretty much wraps up this particular discussion. I hope it's more clear to you what we are doing with acid-base. If you guys are going to be future doctors, I emphasize a great majority of your question in your MCAT deals with acid-base chemistry because acid-base chemistry is so important in terms of our physiological nature, body chemistry. It's critical.